This lecture is a reaction called Claisen reaction, in which instead of using aldehyde and ketone as you saw in aldol reaction, we're going to use esters to do very similar reaction. So in here we're doing esters instead of aldehyde and ketone, and overall reaction looks like this. You're going to take an ester that has an alpha proton next door, and you're going to use some kind of base to form an enolate. And in which this proton has been removed. And then depending on the reaction condition, you're going to react with another ester. And you're going to use this as an electrophile, and this is going to be your nucleophile, and you're going to form another carbon-carbon bond formation like you did before. And the product that you're going to get is actually with the, so that's the nucleophile ester, and then you're going to make a carbon-carbon bond formation with this carbon. And so the overall product is very similar to aldol, but notice that you get a instead of alpha beta hydroxy, which is what you got for aldehyde and ketone, now you're getting a beta carbonyl ester as the final product. Alright, so we'll go over the detailed mechanism of how this reaction works, but before we do that, why are these condensation reactions so important, aldol and Claisen? And I alluded to before is that a lot of these condensation reactions, carbonyl condensation reactions, are among the most widely used reactions in biological world. For assembling carbon-carbon bonds, for example, in making steroids, terpenes, cholesterol, fatty acid, etc. So the common source of carbon atom is acetyl-CoA, which is a thioester of acetic acid and a thio group of coenzyme A. I believe I showed you this before, and sorry this is so faint. But basically the important part is the acetyl part, and notice that that is attached to this thio group, and this whole thing is a coenzyme. We abbreviate it as acetyl-CoA, but basically this, you could think of this whole big molecule as a source of 2 carbon long process. What happens in biological world is a reaction is catalyzed by an enzyme called thiolase, in which one acetyl-CoA is converted to its enolate and then reacts with the on second molecule of acetyl-CoA, just like you've seen before in the Claisen reaction that you've seen here. So briefly, I could just write down what happens in nature is that we have, and I'm going to abbreviate obviously, we're going to have acetyl-CoA with another acetyl-CoA. One is going to serve as the nucleophile, one's going to serve as an electrophile, and is catalyzed by an enzyme called thiolase. And you're doing a Claisen reaction in which the product is this. So in other words, let's say this is the enolate, then it reacts over here, and this is removed, as we'll see later. But notice that this carbon-carbon bond formation is made at this point. And then another reaction happens in which an enzyme called synthetase now reacts with another molecule of acetyl-CoA, and that serves as the nucleophile, and then it goes and does the aldol reaction, in which this enolate goes and attacks over here, so that what you get is an alcohol at this carbon. And like all enzymatic reactions, this is done chirally. So this part is exactly the same. This carbon is now made a carbon-carbon bond with this enolate. To make this carbon-carbon bond. So notice, in these two enzymes, its job was to do a Claisen reaction in the first step, and then the second step is an aldol reaction, where the enolate of the acetyl-CoA, it reacts at the ketone part of this compound, and so this is how it keeps growing in building the carbon framework that it needs to build whatever that is building, maybe fatty acid or cholesterol or steroid or terpenes or whatever it is. Okay, so you'll see when you take biochemistry, you'll see a lot of reactions that you learn in organic chemistry over and over again under different context, in that it's going to be enzymes that make the transformation happen, but what the reaction itself is very similar to what you're learning in organic chemistry, which is if you learn Claisen reaction and you know the transformation, and you could apply then to biochemical transformations. All right, so let's take a look at Claisen reaction more in detail. We looked at the overall reaction, but basically this should be very familiar to you since you know aldol. So you have some kind of base, and a side note about the base is that since we're reacting with ester, if you can't use hydroxide, sodium hydroxide or potassium hydroxide as the base, because then you'll do a saponification. And if you do saponification, then you get a carboxylic acid, as you know, and then that carboxylic acid produces an acidic proton, which will get deprotonated. Remember, this saponification is the reaction that that you learn in making soap. So that acidic proton is deprotonated, and you get a carboxylate salt. All right. So this reaction will not happen if you react with a hydroxide ion. So instead, you react with an alkoxide like this. And the alkoxide that you want to use is the same ester alkoxide, so that even if esterification happens, you don't get a trans-esterification. Like if you react this with a methoxide, then some of this would turn into methyl ester instead of an ethyl ester. All right, so here's a base. It's going to deprotonate the alpha proton and form the enolate. So here's an enolate resonance stabilized by having negative charge on oxygen. So this is the enolate that it forms. And because this base is not a strong base, we have an equilibrium as shown here. So we have a lot more of the starting material than the enolate. So a mixture is present in this reaction. So that means that with the enolate present, you also have unreacted ester present. So then self-reaction could occur in which this is going to serve as my nucleophile and the unreacted ester is going to serve as an electrophile. So the enolate is attracted to the carbonyl, and as you've seen before, the reaction occurs between the alpha carbon with the carbon of the carbonyl of the ester to form this bond. And notice with this is a different intermediate than what you saw in aldol reaction, in that when the O- forms, it could come back down, and now you have a good leaving group. So remember, in aldehyde and ketone, you did not have a good leaving group. You had either an R group or a hydrogen group in here. So this chemistry did not occur, and this is really the basis of the difference in chemistry of aldehyde and ketone in Unit 2 versus the acid derivative chemistry, in which when you have acetyl vinyl reforms, the leaving group leaves, you are making an acyl substitution reaction. So that's why the double bond O forms and this bond has been made, and that is the initial product. So notice the initial product though is alpha beta is a dicarbonyl compound. So this proton right here is going to be very acidic, as you'll see in the next step. So the next step is that the initial product that you form doesn't stay this way, because this is very acidic proton, even more acidic than the proton that you deprotonated in step 1, because the pKa of this is over 20, whereas this pKa is 9. So as soon as this forms with this base around of pKa of 16, it's going to be deprotonated, and you're going to form this stable beta ketoester anion, which is going to stay that way. And notice the base is not regenerated, but because it grabs the proton, it becomes neutral, which means that a full equivalent of base is needed in order to carry out the reaction. So then this is actually very stable. So notice the equilibrium is driven to the right, because this anion is stable, resonance stabilized by 2 carbonyls, it wants to form, and so the reaction is driven to forming this product. So then in order to get the neutral product, you need to get this protonated, which is the last step with the acid, and then you form this neutral form, which once again, because of the 2 carbonyls, it will exist in a keto form as well as the enol form, and so we'll have a mixture of these neutral products as the final products. All right, so that I'm going to stop here before we move on to the next step.